So now we're going to begin a really important topic in chemistry. It's all about moles, but not this mole. The mole is the term, it's actually a unit, and it's a unit to help us describe a large quantity of something. It turns out that this amount contains this many atoms. So if you group this many atoms together, it can be called a mole. Now, it doesn't just have to be atoms either. It can be this many molecules, we still call it a mole. It can be this many ions, it's still called a mole. This many formula units, it's still called a mole. This number of anything is called a mole of it. And we use it when the ratios matter. Remember, we've been talking about how things need to be whole number ratios of atoms. And when you do reactions, an entire atom reacts with another entire atom. It's not like you have half an atom or a quarter of an atom. But the problem that we have is if you can imagine a piece of charcoal, like a briquette of charcoal, just, that you can hold in your hand, that contains this many atoms. And that's like a normal size, amount that you would use in like a little lab, that little brick. So how do we write papers and how do we talk to each other and get around having to say, so I took 6.022 times 10 to the 23rd atoms of sulfur, and I reacted it with 32.00 times 10 to the 23rd atoms of oxygen. And imagine if instead of small little elements, we were talking about like pieces of DNA or something like that. It gets really cumbersome to talk about things in terms of times 10 to the 23rd. It also gets to a point where like we can't really understand the quantity we're talking about. If I say 6.022 times 10 to the 23rd, and then I say, 12 times 10 to the, 46th, is that double? It's not double. To double this number, I multiply this top part by 2. So if I'm going to double that, this is that number doubled. So kind of the math gets a little funny when you're dealing with exponents, like it's just not as natural. And then something else that happens is just like that understanding, if you are trillions of dollars in debt, it kind of doesn't sound that different or mean anything differently than, being $1 million in debt, really, right? So, if we talk about things in terms of moles, it makes it a lot easier to see things like, oh, instead of it being 6.022 times 10 to the 23rd of one thing, and, 12.01 times 10 to the 23rd of something else, I'm taking 1 mole of sulfur and 2 moles of oxygen, and they're stuck together. It becomes so much more clear that I'm talking about SO2 rather than when I'm talking about atoms. So then you're like, well, why did someone pick this amount? Well, I'm sure there's lots of reasons. They had to pick some element to standardize it with, and the one they picked was carbon. Of course, carbon's everywhere, so it's a good one to pick. And this was actually debated in the as late as the 60s. There were people who thought other elements should be used as the standard, but it was finally ultimately decided that carbon would be standard, and they took pure isotopes of carbon-12 and weighed out 12 grams, and they figured out and they verified that it was 6.022, and there was all these other numbers that come after it, times 10 to the 23rd atoms. Now, of course, back here when he was deciding all of this, he got to pick the elements, he got to pick what he was doing with it. If you think about it, he wasn't dealing with a chemical factory. He wasn't dealing with that kind of a scale. If you've ever seen factories running chemicals through, they've got vats and vats of like chemical processes and like reactions going on, and they're huge. He wasn't dealing with that. And they also didn't have this like tiny electron, like microscopic scale chemistry, like teeny, tiny, tiny amounts. They didn't have the equipment for that. So they just worked in amounts that were like, like palm size. That's like a normal amount of something to work with. So that's where the kind of this idea of a good amount to use or a good something to use for these atoms, that's one of the reasons behind it.